All right, guys. So I just want to kind of draw comparisons to what we did yesterday, because if we can recognize that this proof is very similar to yesterday, we can probably approach it the same way, or almost the same way. Remember yesterday what we did is we started off over here saying that AC was the same thing as BD, right? That's what we started off with, and then we removed that common feature of BC, and that left us with that argument there that AB was equal to CD, right? Okay. Look at what today is. Today, it's small right now. It says AB equals CD. So we start with that. Okay. They start with the green equal to the blue. And they ask you, can you then figure out that that purple one would be the same as that yellow one? Does that make sense, everybody? Okay. So yesterday, it was a subtractive idea, right? We subtracted BC from both those initial equalities, AC is equal to BD. Now, we're going to add something, okay? It's ultimately a very similar proof. There's one kind of different defining step, but this is still, you remember yesterday I called this the common segment theorem. This is actually going to be kind of the better version of the common segment theorem. We'll talk about it when we're done. But AB equals CD. We start off with that information right there. Okay, so write that down. AB equals CD. Given. Right now, this is a situation. This is one of those proofs that maybe we have to look at the proof statement first, or before we start working, to recognize what we're going to try to do here. Our goal, if we look at AB equals CD, we want to get to the fact that AC is equal to BD. You guys, just somebody give me a number. 7. Okay? So we get that number there and that number there to be 7. That's kind of what the idea here is. If we start off with that information, give me another number. 4. So let's say B is 4. Would it be easy to make the jump then that distance right there is 11? Right? A to C is 11. Is B to D also 11? Okay? Would you say 11 is equal to 11? Would you say then that AC is equal to BD? All right, so that's doing that with a specific case. So we do that with the general case. Okay? So what we have to think about is essentially that segment right there first. How do I deal with that segment? Well, I'm going to name that segment, or call that segment, AB plus BC equals AC. Would you guys agree with that? Okay, and that's just right along the lines of what that handout I gave you Friday said. If you have segments in your picture, you're probably going to want to use segment what? Addition. Is that segment addition? Yeah. Okay. So it's the segment addition postulate. Okay. Now, can we say something similar about that segment? With that green one? The new green one? We say that BC plus CD is equal to BD. That's the same way. I'm going to put segment addition again. But that's the approach there, correct? All right. So now, if you were to compare to the question we did yesterday, we were able to basically write, let me see if I get color here. We're able to say that set of addition and this set of addition, we're able to be equated to one another. We're able to put them equal to one another because previously somewhere we had said that AC and BD were equal. Does that make sense? So yesterday we previously said in statement number 1 that those things were equal, so then we were able to set these things equal. Okay? Well, in this problem, do we have these two things to be equal? I look through the previous statement, which is only statement number 1, right? Are these two things stated to be equal in statement number 1? No. A, B, and C, D, right? Those are different than this. So we can't make that conclusion. We can't do right now what we wanted to do yesterday, or that we did do yesterday. Okay? So this is where it kind of turns into slightly different. Okay? We need, erase, there we go. We need another concept. We need another idea here. Okay? Before I write the actual idea, we're going to make some kind of procedural thing here. Some people do it, some people don't when you read their proofs. I want us to get used to doing it. Okay? And if we saw that, kind of that specific case scenario when we used that 7 and 4 values at the beginning, you saw that 4 was added to both sides, right? So 4 was a constant value that was in both sums. That 4 is what's hiding behind maybe these two symbols here. Okay? We just want to tell everybody that what we're about to add is actually the same thing on both sides. Okay? Some people, as authors, say that's in this maybe proof isn't all that necessary. It's kind of maybe common sense or obvious after we write the next statement. Someone's going to say we need that. Okay? It's just kind of a stylistic thing or a particular approach that some people use, some people don't use. I like to use it because I know it's going to help us when we get to chapter 4, where we absolutely need to write down the parts of our picture that are overlapping. I think getting used to doing that now, it'll just be kind of second nature later on. Okay, so BC equals BC, reflexive property. Now what I'm going to do is I'm going to rewrite statement number 1. I'm going to write AB. Now leave a little space here. Equals CD. And that's all number 1 says, right? Okay? So if I rewrote it that way and just left it as that, I'm not saying anything new, and that's kind of dumb. Okay? It's not really useful. We don't want to be repetitive or redundant. But can I do this? Can I add any number that I want to? Don't write this. But can I add any number to both sides? Would be okay? Okay? So I use 4 because that's what you guys told me earlier, right? But could it be 4.1 plus 4.1? Could it be, 410 plus 410? Could be any value I want. Okay? So what we do is we talk about that BC, because that's a distance, okay? That being that any value that we want. Okay, so I'm adding that. You guys said initially 4. Let's add 4 to both sides. Okay. And when we add something to both sides, what's that reason what allows us to do that? Add to both sides is addition, correct? Addition property of equality. We've got to keep that. When I think about an equation, I think about like a balance, okay? A balanced scale. And whatever I do to one side, I make the left-hand side heavier by adding something to it. I got to make the right-hand side heavier too, okay, to keep that balance. All right, so now this is where we can kind of do what we wanted to do yesterday. Because yesterday we had the idea of being able to maybe look at that. Okay, have I named that something else previously, or is there another statement that says that is equal to something else? If we look up, we've got AB plus BC right here, right? What is that statement also equal to? See that? Okay. So AB plus BC, previously we've said it is the same thing as AC. So let's write that. Have we said that CD plus BC is something else earlier in the proof? Yeah, it's BD. Now, we have to understand that we have the associative, the commutative property with addition. So we're going to flip-flop that. So CD plus BC, same thing as BC plus CD. But that right there is that which we're saying is equal to BD. Let's replace it with BD. So removing AB plus BC and replacing it with AC, and removing CD plus BC and replacing it with BD, what's that replacing procedure called? Okay? Is that what we want to prove? Yeah. Okay. Now I'm going to show you something that we're going to use later in this course. We're going to have overlapping triangles. Our goal will be eventually to show if those triangles are congruent. And there's a lot of things that are necessary to do that. But one of the things that is necessary to do that is that we need to be able to show that segment there congruent to that segment there. Would you guys agree that those are the sides of those two larger triangles? Okay? They're a set of sides. We need to show that those are congruent. Well, what the text is going to provide us, and what the question is going to provide us initially, is just that part right there and that part right there are congruent. Does that make sense? So hopefully you can see or recognize that is simply doing what we just did. If they start us off with that equal to that, and we get from there to there, or that red segment, to be equivalent to there to there, or that blue segment. Does that make sense? Okay? So inside this proof, guys, when we get to this in chapter 4, inside that should be these 5 steps. Okay? Now, in the event of doing that triangle proof, if I incorporate these 5 steps as these 5 steps of that triangle proof, that might be a 15-step proof. Okay? Because of these additional 5. It would be really nice to kind of shorten those. If they said 15 steps, let's just call this the common segment theorem. Okay? And then later on, when we then get to, we get to this, and I need to show that A, C is the same thing as B, D, I can just make that jump right away. And it is one step that I can use one step. So I would automatically say in that proof that AC equals BD, and my reason would be the common segment. We're off the page here. My reason would be common segment theorem. And that encapsulates those 5 steps as one step. Does that make sense? And that's the benefit of being able to recognize proofs, but then at the same time kind of storing those and keeping those in the back of our head, because that proof might be used collectively inside another proof. All right? If we can hopefully start doing that kind of thing, we'll be able to navigate some of these concepts pretty easily. All right, so that's the common segment, and again, that's kind of the version that we're going to use the most, where we're using that additive property, okay, instead of the subtraction one that we did yesterday. But they're both referred to as a common segment here. All right, let's do this one. I just want you guys initially here to write down your given, okay? And we see some vocabulary up there, right? Okay? I want you to write down what you gain from your vocabulary. All right? I'll give you about 3 or 4 minutes to do this. And then we'll come back and talk about how we address that and how we approach that and if we did it correctly. Okay? So give you a couple minutes to do that. Something else, guys, to think about when you're doing this, just kind of a organizing approach. There's multiple pieces of information up here in the given, right? my suggestion is you don't have to number them all separately. But I would write like angle 1 and angle 2 are a linear pair. And then underneath that, I would write KI bisects HKJ. Because I think it's a little bit easier to recognize that you got multiple things going on there, where if you did it this way, you might overlook one of them. Does that make sense? Okay, so try to organize the way you do these things, I think in a kind of logical, thoughtful manner. So where we're at, we'll kind of stop and discuss what's going on here. We got a linear pair, right? That'd be the first vocabulary word in the given, okay? We're going to address that, and we're going to kind of exhaust all the statements that provides to me, okay? And we'll write all those down, and then we'll go back up and we'll look at bisects, and we'll exhaust everything that the bisects tells us. Does that make sense? Okay? And this is the first time that maybe we've seen this, and I think we got to talk about it in detail because we don't want to get people lost. Okay? When we say linear pair, okay, did anybody put measure of angle 1 plus measure of angle 2 equals 180? Nobody put that? Okay, that's good. Okay, so what'd you put then for statement number 2? If they don't equal 180, what'd you say? Anybody say angle 1 and angle 2 are supplementary? Okay, let's think about this. When we use our vocabulary, okay, we would want to know what that definition is, right? If I go find that definition, all right, and remember, when we're doing these proofs, we're using deductive reasoning, okay, so we're using information from previous facts. So we should have seen this at some point throughout the year so far. So I go back to section 1.5, and this is where we introduce the vocabulary word linear pair. The linear pair is a pair of adjacent angles whose non-common sides are opposite range. It says anywhere within that definition, say anything about supplementary or the number 180. No. Okay? It says opposite range, right? Okay? So that vocabulary word doesn't really lead me anywhere yet. But look down there in that postulate. It says that two angles form a linear pair, which is what we're saying, right? And those two angles are what? One of supplementary. Okay? So this is the one, it's one of the few times, okay? I'm not going to say it's the only time, but it's one of the few times where this vocabulary word, it does lead me to something. It leads me to angle 1 and angle 2 are supplementary. Okay? But the reason isn't because of the definition of that thing, right? Because that supplementary word was not found in the definition. If you go that route, yes. If your definition goes off of the linear pair, incorporate straight angle, yes. But then you have to define what a straight angle is. Does that make sense? So that is an option, yes. Okay. But I want to show you this way because this is the way that most in a course exam or other textbooks, other geometry courses are going to address this. It says angle 1 and angle 2 are supplementary because that is presented inside, not the definition of a linear pair. It's provided inside the linear pair postulate. Okay. Now, what do we do when we made this statement? We created another vocabulary word, didn't we? All right, so this linear pair creates this statement. That statement creates another vocabulary word, so let's keep rolling with this new vocabulary word. What supplementary means for our specific case? Yeah, now we say measure of angle 1 plus the measure of angle 2 equals 180. And that's the definition of supplementary. Here's the logic behind these proofs, guys. When somebody else is reading my work, and they're not maybe as versed in the geometry or the algebra that we are, or as well as we are, we should be able to give them a statement, and they should be able to go look inside the textbook or inside some type of other document, other publication, and say, okay, they made this statement, so I should be able to look over here in this column and look for that object inside that text. Does that kind of make sense? So let me give you an example. If I say linear pair, okay, and I go angle 1 and angle 2 are supplementary, they should be able to look in my text, look for linear pair, and eventually get to, pretty quickly, the fact that they're supplementary. And they get through that fact by looking, if they look up linear pair postulate, it's going to tell them that about angles 1 and 2. Does that make sense? Then when they look up supplementary, they're going to say, okay, well, that means 180 degrees when I take the two angles down together, so that gives them this statement here, okay, by looking up the definition. If I go straight from linear pair straight to 180, and they open a textbook, and it says linear pair, it provides that phrase right there. Terrible job of circling it. If it says that phrase right there, nothing up there says the number 180, right? So then they get lost. There's a gap in the understanding. There's a gap in our logic, okay? And we don't want to make assumptions that they know how to fill in that gap, right? Okay? We need, you hear me say this, we need to hold people's hands. We need to drag them along through every single step so that they don't get lost, all right? Now, that being said, you heard me say yesterday that these things come in clusters. These statements come in clusters. Every time you see the word linear pair, you're going to say, okay, what angles are we talking about? 1 and 2. We then say that they're instantly supplementary. And then we write the algebra that goes with them. So these three statements, okay, now it might not be angles 1 and 2 right now, or sorry, later on, it might be angles 4 and 5, or whatever, or they might give names for them. But if you say that they're a linear pair, you instantly say that those two angles are supplementary, and you can instantly say then that when we add them together, we get 180. Is that right? So that cluster of three statements always goes together. Okay. So now, not exhausted that definition. But we've got another one, don't we? Bisects. Okay. So what's bisects provide me? If I look at my picture, what's that going to tell me about some information up there? Okay. Absolutely. Measure of angle 1. Measure of angle 1 equals the measure of angle 2. Okay? Because that's what a bisector does, right? An angle bisector creates two angles that are congruent, and if they're congruent, we know that their measurements have to be the same, right? So this is the definition of, I'm going to write angle bisector. If you do write bisector, that's okay. And that's everything from our given, guys. That's everything that we need. Okay? If you want to go in your picture, I think it does make sense to do this. Okay? Now think about this. Think about logically what we've done. These two angles add up to 180, but they both have to be the same, right? So what does one of them have to be? No, the only way that they can both be the same and still have 180 is if both of them are half of that 180, right? Okay? So that halving idea is going to kind of show itself in the next couple steps. Okay? We want to prove that angle 2 is a right angle. Okay? So I'm going to go through some algebra here that just leaves us with angle 2. I'm going to take statement number 3. I'm going to rewrite it. I'm going to rewrite it so only measure of angle 2 is showing up. All right, obviously, plus measure of angle 2 equals 180. I want this measure of angle 1 that is right here in step 3. I want that to go away. What can I replace that with? What do we say measure of angle 1 also is? the same as measure of angle 2, isn't it? Can I go where I see that in this statement? Can I replace it with measure of angle 2? Is that okay with everybody? So statement 3 and statement 5 say the exact same thing, but I pulled out angle 1 and replaced it with what it was equal to, right? What is that process called? Substitution. All right, now the rest of this is just algebra. Remember, this is measure of angle 2 plus measure of angle 2. Those are hidden numbers, right? There are numbers behind those symbols. So are those like just variables? All right, but they're just, we can use, maybe you even did this like in 7th and 8th grade. Like when they first introduced what a variable is, they would put like an open box somewhere. They say open box plus 5 is equal to 7. And then what has to go in that open box? 2, right? Okay. So they're saying that open box is a variable. Okay. Would that be the same thing there? Do I still get 2 for that x if I rename that open box? Does that make sense? Okay. And then they made a progression like open boxes and stars and triangles and stuff like that. And they say, okay, well, those are symbols. Now we're going to use x. Okay. Well, it's the same idea. Okay. This is just a better variable, a better representation because it is indicative of what we're solving for when we're done. Okay. If you want to call it x plus x equals 180, by all means, that's fine. Okay. So if it was x plus x equals 180, how would you rewrite that? You rewrite it as 2x, wouldn't you? 2x equals 180. So if it's measure of angle 2 plus measure of angle 2, aren't you going to rewrite that as 2 measure of angle 2s equal 180? All right, and I'm going to call it combined like terms. Distributive property if you want. And now you can maybe see, now where that halving idea comes in. I don't want to know twice the measure of angle 2. I want to know what one measure of angle 2 is. So what do I need to do? Divide both sides to get measure of angle 2 is equal to 90. Division. Okay. Now remember what we're saying here. When somebody reads this, we should be able to allow them to go from step 1 all the way through the end and reach the conclusion. When I say measure of angle 2 equals 90, if the person that's reading our stuff isn't as versed as we are, they don't know that's the right angle, right? So we need to go one step further. Now that I know that it has this characteristic, okay, my statement number 8, I apologize for kind of running off the page here. My statement number 8 has to now be angle 2 is a right angle. Because now that matches what I wanted to prove, right? What allows me, think about this, we talked about this. I looked at measure angle 2 equals 90. That is a characteristic of an object. What allows me to look at characteristics, okay, this thing has this particular quality or characteristic, and because I have this type of statement, I can now categorize or identify what that thing is based off that characteristic. What are those statements that allow us to do that? Types of statements that allow us to categorize, identify, are called what? How did I know when measure of angle 2 equals 90? How did I know that's a right angle? Say again? It's the definition of right angle. When you look at something, when you take a characteristic of an object, and then you take that information and say, now I can categorize this object as being right, or maybe I can categorize this object as being isosceles or whatever. When you're categorizing, you're doing that based off of what the rules are defined as inside the definition. Okay? So when we bring in a vocab word, most of the time it's going to be because we know the definition of that vocab word. Okay? That's the only way I'm allowed to classify something, right? The only way I can call you guys sophomores or some of you freshmen, is if I know what the definition of a sophomore is, right? Okay. The only way that I can call that thing when measure of angle 2 equals 9, the only way I can progress to the fact that it is a right angle is by knowing that that information is encapsulated inside the definition. Okay. There's some steps you got. I said first 3 steps, they come as a cluster. We see linear pairs. Those 3 things are going to come over and over and over again in the proofs that we go through. Okay. Once we introduce statement number 3, okay, the practice that we went through to try to replace something on the left-hand side is a very common practice. So I have measure of angle 1 plus measure of angle 2 equals 180. We replace one of those 1 or 2s, right? That's a common practice throughout these proofs. Okay. It'll be eventually where we replace both 1 and 2. Okay, but it's very similar things occur inside other proofs. So that's why I want you to have these written down. I want you to be able to look at these and reference them. They can provide you tips for doing maybe a problem that's completely new to you. All right, let's go. We'll do one more. We'll be done. Let's do this one. Lose my voice. Don't get excited, Britton. All right, so this one, write your given down, right? What you get from the vocabulary word up there. I like this one because it shows a little, procedural thing that we need to talk about. When we write our given down, there's quite a few things in there. There's the fact that we get a right angle, right? So I should probably draw that in my picture. I do that with that little box up there ahead. We also get the congruency of angle 1 and angle 3, right? My hopes are when you saw the vocabulary word right angle, did you write this? Measure of angle WXY equals 90 degrees? Because that is what is encapsulated in that definition. When I look up or I Google right angle, okay, the definition of right angle, it's going to fit back that it is an angle who has a measurement, has or is measured at 90 degrees. Okay, so we write that specific information for our problem. Okay, now we'll walk through, we'll keep going, the definition of right angle, but before we go through and get step 3 and 4 and 5, let's just kind of think about this logically. Give me a number less than 90 degrees. Say again? 89. That's the one we used last year. 89 degrees. So if angle 1 is 89 degrees, what's angle 3? 89 degrees. Then what's angle 2 got to be? If 2 and 3 are complementary, or they create that right angle. Got to be 1, right? Does that prove to you what we tried to prove here, that 1 and 2 are also complementary? Or 1 and 89, let's compare that angle there and that angle there. Are those going to have to 90 degrees? Yeah. And no matter what you choose, if I choose angle 1 to be 70 degrees, then this one's 70, and that one's 20, and then 20 and 70 are 90, right? Does that make sense? Okay. This is actually, there's going to be a theorem in a couple, maybe tomorrow, about this idea. Okay. That allows us to kind of get to this conclusion a lot quicker. All right, so one thing that we're going to need here is to talk about, we want to do some algebra, okay? And if we're going to do some algebra, we can't do that with angle 1 and angle 3 right now, the way that they're presented, okay? Because this is a shape congruent to a shape, meaning that they cut and paste and land on each other. But there are no numbers here. Does that make sense? Okay? these symbols are representative of a image, okay? But with the definition of congruency, we know that means same shape, same size. So then, because they have the same size, we can say that this is true. And that's kind of a procedural thing that we're going to do all the time. When they introduce a congruency, and I want to start doing algebra with that stuff, I got to convert it into the numbers aspect of the relationship. Okay? Because I can't start adding and subtracting and multiplying shapes, right? That doesn't make sense. What's an angle plus an angle look like? I don't know. I can do a number plus a number, right? Okay? This idea, I'm going to always refer to it as definition of congruency. We've already seen it written once in our previous example. The computer, the author had already written it, and they wrote it this way. They said that congruent angles have equal measurement or measures. And all that is, guys, if I were to look up in the back of the book or maybe change our definition of congruency a little bit. Congruency means same size, same shape. Well, same size means that their measurements have to be equal, right? So when we say congruent angles have equal measures, that's the definition of congruency. That's a version of that definition. Okay. A lot of texts will, especially Math Excel and anything written by Pearson, will write this out as the definition of congruency statement. All right, so let's keep working here. Can I say, and we can go off the looks here. Okay. Last class we did this in 2 steps. If we go off the looks up here, because of what we know about this right angle, what can you say about angle 2 plus angle 3? What are they going to add up to? They're going to have to 90 degrees, right? Measure of angle 2 plus measure of angle 3 equals 90 degrees. And that's the definition of 2 angles after 90 degrees are complementary, aren't they? Complementary. Okay. If this is another option, okay, because if I say definition complementary, maybe my person reading my proof doesn't really where they get how do they know that's complementary? Could this also be angle addition? You know the total should be 90, right? Do you know the 2 smaller angles add up to give me that? Are they adjacent angles like that that work through the angle addition process? So we'll call that angle addition process. That's fine. Okay, and that's something about some proofs, guys, is that there might be multiple ways, multiple reasons of logic that allow me to get from one argument to the next. Okay. All right, so if I've got 2 plus 3 equals 90, what do we have up here? We have 1 equals 3, right? Can I do something there? If 1 is the same as 3, can I rewrite statement number 4 using that fact? So let's take statement number 4. Let's take that 3 out and replace it with 1. Is that okay with everybody? So substitution. And the idea here, guys, is, you might be thinking, well, he knows what he's doing. He knows the steps are. This is the second time I've done this proof. Okay, I did it with first period, and that was the first time I did it with him. Okay? I'm just being able to recognize kind of patterns that I've seen in the past, and I know that once I have, kind of like we saw the last one, once I have a phrase that says we have addition equal to a total, I know a general procedure, a general idea is to be able to replace one of those parts or both those parts. So I'm just trying to see, okay, is there anywhere that I've rewritten or re-identified angle 2? I haven't. So is there anywhere then that I've rewritten or re-identified angle 3? And I have. So then I know I can put those together and create something new. Whether that new fact is going to be helpful or not, I don't know. Okay? But now that I read that, you have 2 angles that after 90, right? What can you tell me about angle 2 and angle 1? Verbally, you would say angle 2 and angle 1 are complementary. Okay? Because now we just classified something, right? We just organized it that fits this relationship, this characteristic, this quality. So that's the definition of what? Complementary angle. Okay. Hopefully within the